Here's another video for the lecture intropde. In this video we start with chapter 5. This is the last chapter, and in this chapter we solve the wave equation. We will solve it for the dimensions with different formulas. Yeah, so we will start with the lowest dimension in section 5.1, which we present today. We will solve it only for dimension 1. So this means one space dimension and one time dimension. So the differential equation is this a wave equation. So we write it, we may write it in this form. U depends on x and t, and we take the second time derivative, subtract the second spatial derivative, and now we start with the homogeneous wave equation. Yeah, homogeneous wave equation. And of course x and t are both real variables, so typically we assume that t is non-negative. And again, we may think about this, we may conceive this as an ODE on the space of functions depending on x. ODE of second order on the space, infinite dimensional space, of course, of functions depending on x in real variable. Yeah, and since it's second order, the initial value problem, the initial value problem fixes or assumes that u of x and 0 and u du by dt of x and 0 take some given values. Yeah, because if we consider this as such an ODE, then the initial value problem means we should fix in this vector space, so in this space of functions depending on one real variable, first the value of this vector, so of this function, and the first derivative. Yeah, so these are these two things which we fix. So we assume, we look for a solution of the following initial value problem. And in fact, this is not dependent on the dimension, so for any dimension, later we will see for the look for the analogous initial value problem. So we have the differential equation, the homogeneous. We first start with the homogeneous differential equation is equal to 0 with u of x0 is given by some function, and du by dt of x0 is given by some other function, h of x, for given functions g and h. Okay, this is now the problem which we want to solve, first in dimension 1, and later we will do it analogously for higher dimensions. Now for dimension 1 there's a crucial observation, namely that in this case, but only in this case, the wave operator, so what is the wave operator? As we call the operator d by dt square minus d by dx square, wave operator. Yeah, I should write it small. And in dimension 1 it factors. Yeah, in dimension n equals 1 it factorizes. Yeah, we may write d by dt square minus d by dx square. This is of course the same d by dt plus d by dx times d by dt minus d by dx. Yeah, this is true since this partial derivatives of course commute. Yeah, if the solution should be of course twice differentiable, and then the partial derivatives commute. And now this is, we may use this factorization. Use this factorization in order to simplify the wave equation, but only in one dimension. Yeah, the wave equation in dimension n equals 1 to two different first order PDEs, and in fact to two versions of the transport equation, which we solved. So we may solve this equation by this method. This gives a solution. Okay, now let's do this. Yeah, and the idea is now quite simple. Yeah, if we have this equation, so we now have the equation d by dt plus d by dx applied to d by dt minus d by dx of u of xt is 0. So what do we do? Yeah, now we call this as a new function v of xt, and so we define v of xt as du by dt of xt minus du by dx of xt. And then we have clearly dv by dt of xt plus dv by dx of xt is 0. So is 0. But then we know, that this initial value problem we have solved. The corresponding initial value problem we denote the corresponding initial value a of x. So this is v of x0. Yeah? And of course, by this formula, this is du by dt of x0 plus du by dx of x0, and this is then h of x plus dg of dx. Okay, this we also may write as g prime, because g is a function only depending on one variable. Okay, but we solved this transport equation. Maybe I I recall this, I show you the formula. Yeah, this was in the very beginning, the transport equation, the homogeneous transport equation. Yeah, so here B in our situation is of course just 1. Yeah, B is 1, and then we have, this is the solution, so we have, yeah, here, this is the solution, so we have V of xt is equal to A of x minus, since B is 1, t. Yeah, this is the solution. Okay, and then we may write this is h of x minus t plus dg by dx of x minus t. Okay, now we want to proceed. Now we want to solve u. Yeah, of course, we only have solved so far v of xt. Now, if we insert this, now let's insert this. Yeah, here we insert now this equation. So what we get? So we get du by dt of xt minus du by dx of xt. Yeah, this time minus is equal to a of x minus t. Let us first don't insert here these values. This we will do later, yeah, to simplify. Okay, this means now we have, this is the inhomogeneous transport equation, yeah, which we also solved. Yeah, so let's look here. The formula for the inhomogeneous transport equation. And so this is here the formula. Yeah, this is our formula. So we obtain u of xt is equal initial value, this is of course g of x minus b, b is 1 minus t, plus integral over the inhomogeneity, which is of course this function here, integral from 0 to t of a of x plus s minus t. And in the second variable, we should just insert minus s. Yeah, sorry. Also, if we insert here for t s, then we get a minus s. Yeah, so we get minus s ds. Yeah, and this we may simplify. So this is g of x minus t plus integral from 0 to t x plus s minus s. This is just a of x minus t. No, there's something wrong. S minus t. This time b is minus 1. This is my mistake. Yeah, this time here for this b is minus 1. Yeah, since here we have a minus, so b is minus 1. Yeah, this is my mistake, and for this reason we have here a minus. Minus, and then we have here, so if we simplify this, then we have a minus 2s plus t ds. Okay, and now let's return to our section, to the wave equation. Okay, so So yeah, so this is this integral here plus b, but b is of course just the same as g of xt. Okay, and then we may write this. Yeah, now we substitute. We call y is equal to x minus 2s plus t. And then we clearly have that dy is equal to minus 2s. And for s equals 0, as y for s equals 0, what comes out? Then we have x plus t. And for y, when s is equal to t, when this is, then we have x minus t. And now, in order to get rid of this minus, we just switch the two borders, and then what we get, then we get that this integral here, this is equal to g of x minus t plus integral. Now here we start with x minus t to x plus t, and we should insert our formula and we need an addition in factor 1/2, to cancel this factor. Okay, and then now we should insert this here. Here it should be a plus moment. Why this is a plus? This yeah, of course. Yeah, since this time here, this time b is minus 1. Yeah, so this should be a plus. This should be a plus. Sorry. Here for the second transport equation, inhomogeneous transport equation with b equals minus 1. And so we get here always a plus, and here also a plus, and then we insert this integral. We know that that the function a, now we call what is a. A is just a of x is just h plus derivative of g. So now we insert that a is h plus derivative of g, then we get h of y plus, no, it should be minus sorry. Here, this is the definition. So there's again a mistake. So this should be minus. Yeah. Okay. So, and then here, this should be also a minus. Okay, so now we arrive at this formula. This is now a minus g prime of y dy Yes, this is our solution. And of course, this, now we may use the fundamental theorem of calculus in order to determine this, and then we get g of x plus t plus 1/2 integral x minus t x plus t h of y dy. And here we get minus 1/2 and g of x plus t minus g of x minus t. Okay, and if we now combine these terms here, yeah, then we see this cancels, so we get 1/2 of g plus x plus t plus g of x minus t plus 1/2 integral from x minus t to x plus t h of y dy. Very nice formula. Yeah? So this is now called D'Alembert's formula. Yeah? This is D'Alembert's formula. Yeah, which solves the initial value problem of the one-dimensional wave equation. Okay, and we know that this is the unique solution. This is the unique solution. Yeah, but of course only if h and g are differentiable, twice differentiable. Yeah, if g is twice differentiable, and h is continuously differentiable. Yeah, because then the integral clearly is twice differentiable, and so the whole function is twice differentiable. Yeah, so this is D'Alembert's formula. Okay, so one directly sees, in all, in particular, all solutions are linear combinations of functions depending on x plus t and functions depending on x minus t. Yes, so they are of the form f of x plus t plus g of x minus t. Yeah, and this is nothing else but the consequence of the factorization. Yeah, this is again a factorization. This solves the equation. These are the solutions of the equation d by dt minus dx, d by dx, f is 0, and these are the solutions d by dt plus d by dx, g is 0. So this is the explanation why they have this form. So this is, and now there is another important observation. Yeah, with this formula, we see that the value u of xt depends only on the values of g at x plus t and x minus t, and the values of h on the interval, yeah, x minus t, x plus t. And this we interpret, yeah, if we draw here x and here t. Yeah, and if we have some point xt, here is t0. So we have here some point x and here some point t. Yeah, then we see these are the values. This is the value x minus t, and this is the value x plus t. And this is the interval in between. Now, if we look at the straight lines going from any such point here, all these straight lines, for all these straight lines, the difference of the time is smaller than the difference of space. So all these lines correspond to movements with velocity bounded by 1. Yeah, since the space difference is always smaller than the time difference. Yeah, dx is smaller or equal dt along all these lines. And this means the movement, the velocity is smaller or equal to 1. Yeah, and the absolute value of the velocity, maybe we should say. Okay, so we interpret, so the solution, the solutions propagate with velocity bounded by absolute value 1. This is a difference to the heat equation. Yeah? In the heat equation, if you, maybe I recall the formula for the heat equation. Yeah, because for the heat equation we also had x and t. So if we recall the formulas for the heat equation, yeah, u of x and t, this was integral over exponential. Also we had a front factor 1 divided by 4 pi t n half, exponential of minus y minus x squared divided by 4t f of y dny. So you see the difference between y and x can be arbitrarily large. Of course, the influence becomes smaller if it's very large, yeah, then the influence becomes smaller. But here, the difference for given t, yeah, the difference of x and y can become arbitrarily large. So for the heat equation, the speed is not bounded. It goes up to infinity. Yeah, and for this reason it depends on all values of the initial values. Even for given time t, it depends on all. Yeah, this is a big important difference. And another important difference is yeah, the solutions of the heat equation, they are smooth and even analytic if for most initial values, yeah, the solutions of the heat equation are smooth for all initial values. Yeah, so the regularity does not depend on the regularity of the initial value. Yeah, of the initial value, as long as it exists. Yeah, as long as the initial value has enough regularity for the existence. Enough regularity for the existence. Now for the wave equation, yeah, we see directly, yeah, for the wave equation, yeah, we see by this formula here, by D'Alembert's formula, here by this formula, yeah, for the wave equation, the regularity depends on the regularity of the initial value. It's more or less the same. Yeah, so the regularity does not increase with time. Yeah, we say the regularity does not increase with time. Let me make one more remark concerning the velocity. Yeah? If we replace h by an antiderivative of antiderivative capital H of h, comma, then how the formula then looks like, u of xt. Yeah, now D'Alembert's formula here, let's see. Yeah. Then this is clearly 1/2, and then we just have g of x plus t plus g of x minus t, and then we have h of x plus t minus h of x minus t. Yeah, so it only depends on the values. Yeah, so this shows that then the velocity is 1. Yeah, so then the velocity would have absolute value 1. Yeah, and we will see that this generalizes to higher dimension, but only to odd higher dimension. Yeah, this will be true for all odd dimensions, but not for even dimensions. Yeah, this is very interesting that one has this different behavior in even and odd dimensions. At the end of this section, we will solve another problem, another initial value problem. It's quite similar initial value problem, which can be solved also for which will show up later in this chapter in higher dimensions. Yeah, this one-dimensional wave equation again will show up, but for this reason, let's now solve this equation. Okay, and what is the difference? We now restrict space to the half line, and we assume a boundary condition. Yeah, so this means we restrict space to the half line. Yeah, we now restrict x element to R plus with boundary conditions u of 0t should be 0. Yeah, so we assume that this should be 0 for t in non-negative. Okay, and the idea how to solve this is a nice idea by reflection, by a reflection principle. So if we have given, of course, we have the same initial value, so I don't write this whole problem. This is just the usual problem, but with this additional boundary. With this additional conditions at the boundary of space, yeah, which is at x equals to 0. Now we define the solution here as by reflecting it. Yeah, we take for negative x, we just take the negative values. Yeah, and if we take the negative values, since the function itself vanishes, we claim that that this u tilde, also we define u tilde of xt by some reflection, so we just define it as the usual one for x and minus u of minus xt for negative. So we extend it by some reflection, yeah, and adding here a minus. Yeah, then I claim u tilde is twice differentiable. Is twice differentiable. Why? Yeah, because okay, essential is that first why we get continuity. Yeah, also since u of 0t vanishes, u is continuous at x at 0t. Yeah, at 0t. Okay, maybe I draw a picture. Here we have x and t. Here is the line, yeah, and here we reflected u of minus xt minus is equal to u of xt. Yeah, this is, we reflect this u tilde of xt as this function. Yeah, and here u of 0t vanishes. Yeah, then of course this is continuous here. Yeah, so then it's here continuous. And if we take the derivatives at 0 and t, yeah, for the derivatives, also d by dx of minus u of minus xt, yeah, this is of course, here we get from the inner derivative a minus and the second minus. So this is the same as du of x evaluated at minus xt. Yeah, so if this derivative, if u of xt, also if u of d by dx xt extends continuously to x equals 0, then u tilde of xt, then this derivative is continuous. Okay, and the second derivative, the second derivative has again to vanish. The second derivative of x. d square u tilde of xt. Now, if we take minus d square dx square of u of minus xt, then we get twice. This is minus d square u of dx square of u of minus xt. So plus the second, so this has to be a plus. And for this reason, no, it was correct. It's a minus, because the second, here we get two derivatives, 2 times minus, and then this minus, so we altogether have 3 times minus. So this is a minus. So this, so u tilde of xt is differentiable if d square u of xt dx, if this limit is 0. So we need this. Okay, and t derivative, of course, doesn't change. So t derivatives, but for the t derivatives, we already have that u of 0t is 0. So this implies that all derivatives, dn by dx n u of 0t is also 0. By t, all t derivatives. Here, t derivatives. They are all 0, of course. And and then they are continuous. Okay, so we extend this, and we also extend, of course, in a similar way, these functions. And then the claim is that that this fits together to a solution of the wave equation on the whole space. So then when u tilde solves the wave equation on r cross r plus 0, and by D'Alembert's formula we get, what we get, so now we just insert, of course, if x, we obtain, we obtain this solution. Now we insert D'Alembert's formula, and then yeah, so what we get as a solution for u of x tilde, now by D'Alembert's formula, this is just g tilde of x plus t plus g tilde of x minus t plus integral x minus t to x plus t h of y, h tilde of y dy. Yeah, and now we may distinguish, yeah, between x smaller or equal to t, or also now we may first we divide this integral. Yeah, this integral we may write, of course, so we get 1/2 g tilde of x plus t plus g tilde of x minus t, and now we have plus, and now we split this integral as an integral from x minus t to integral from x minus t to x to t minus x h tilde of y dy plus integral of t minus x to x plus t t plus x and h tilde of y dy. Okay, and this integral, yeah, vanishes by antisymmetry. Yeah, by antisymmetry of h tilde, so this means h tilde of minus x is clearly minus h tilde of x. Yeah, the first integral vanishes. Yeah, and now, so what is the solution? What we all together get is u of xt is equal. Now we distinguish between when t is smaller or equal to x. Yeah, then when t is smaller or equal to x, then we have 1/2 of g of x plus t, because then the sum is of course positive, because x is now always positive, and if x is if x is larger than t, in the first case x is large, then this is also positive, so this is equal to it. Yeah, plus g of x minus t and plus 1/2, and now we just rewrite as before, x minus t is x plus t, because these are both positive numbers, hy dy. Yeah, this is for x larger or equal to t. But if x is smaller or equal to t, then we get here, of course, x plus t and then minus g of t minus x plus 1/2 integral. And now we replace this by t minus x plus t h of y dy, yeah, for x smaller or equal to t. Yeah, so this is now our formula, and then one sees, yeah, that by this term here, we see that if they come to the boundary, yeah, so if x becomes equal to t, yeah, then the wave is reflected at the boundary. Yeah, we get this other solution which comes from a reflection at the boundary. Okay, yeah, so this is yeah, also maybe I draw here the picture to explain this reflection. Here we have x, and here we have t. Now we have here x, and we have here t. Yeah, then we see this goes here, and so this should correspond to velocity 1, and then it's reflected. Yeah, then it goes here. So we end up at this point, and of course also at this point here. Yeah, so this is the here we are in the situation that x is larger than t, and then we have this is of course the situation where x is smaller than t, yeah, and then we have t minus x, yeah? So this is t minus x, and this is x plus t. Here maybe I erase this coordinate, yeah, and then we have x plus t and t minus x. Okay, and yeah, if now x becomes larger, then this eventually doesn't hit the boundary. So maybe I draw now the picture. Yeah, when x is equal to t, then we have this line, and then it's not anymore reflected. Yeah, this corresponds to x equal to t. Then we have only x minus t and x plus t. And if it's larger, if x is larger, and here we have t, yeah, then we only are in the usual situation, x minus t and x plus t. Okay, so this problem, initial value problem, the solution of this initial value problem, we will use later. So what we have done today, we understood the one-dimensional wave equation. We saw that we may factorize this wave operator, and then we reduced it to a twice application of one-dimensional transport equation, obtained D'Alembert's formula, and finally we also solved the initial value problem, a different initial value problem, which we will also use later. Thank you.